There is a version of Isaac Newton that has become almost mythological. A young man sitting beneath an apple tree, watching fruit fall, and suddenly understanding the universe. It is a tidy story. It reduces decades of solitary, obsessive, and frequently maddening intellectual labor to a single clean moment of inspiration. That version of Newton is false, not in every detail, but in its essential character. It mistakes the product for the process, and the process was nothing like a moment under a tree. The process was years of solitary confinement, self-imposed and rigidly maintained. It was nights spent over furnaces, months decoding ancient manuscripts, and an almost pathological refusal to share conclusions until they had been tested, cross-referenced, and defended against every objection Newton could imagine. And Newton could imagine many. It was a mind that treated ideas the way a fortress engineer treats walls, not as things to be opened, but things to be reinforced. To understand Newton, you have to understand what kind of person builds that kind of fortress. You have to understand the emotional terrain that surrounded the intellectual one. Because Newton's science did not emerge from joy or curiosity alone. It emerged from an inner world shaped by abandonment, rivalry, and a ferocious need to be right, always, completely, and without concession. He was born into absence. His father was dead before he arrived. His mother left him behind when she remarried. He grew up in a household that was not his parents', learning early that the world did not arrange itself around his needs, and that dependence on others was a source of danger rather than comfort. That lesson settled into him and stayed. By the time Newton arrived at Cambridge as a young man, he had already developed the habit of working alone. Not because he was shy exactly, but because other people were, in some fundamental way, beside the point. His notebooks from this period show a mind turning constantly inward, setting itself problems and pursuing them past any reasonable stopping place. He was not networking. He was not socializing. He was building something, a method for understanding the structure of the world. And he was building it in private, with the intensity of someone who fears interruption. The plague years of 1665 and 1666 simply accelerated what was already in motion. When Cambridge closed and Newton retreated to his family home in Woolsthorpe, he did not experience this as disruption. He experienced it as opportunity. The world contracted. The solitude deepened. And in that contracted, deepened solitude, he produced work on motion, on light, on mathematics that would not fully surface for decades, because Newton did not publish it. He held it. He sat on discoveries the way some people sit on resentments, close to the chest, carefully maintained, not ready to be released. This is not how science is usually imagined to work. We tend to think of discovery as naturally reaching toward disclosure, as if truth wants to be shared. Newton did not operate that way. For him, knowledge was something to be controlled, and disclosure was a form of risk. To publish was to open your conclusions to scrutiny, to invite attack, to give others the opportunity to claim partial credit or find errors. Newton found this prospect nearly unbearable, and throughout his life he would repeatedly pull back from the edge of publication, retreating into further work, further refinement, further delay. This is not a story about a genius who generously gave his discoveries to the world. It is a story about a man who built an extraordinary understanding of nature, held it for years, released it reluctantly, and then spent the remainder of his life defending both its conclusions and his right to have produced them first. It is a story about control, over ideas, over institutions, over the people who threatened to challenge him. To treat Newton as a simple discoverer is to miss the thing that actually defined him. The scale of his ambition and the ferocity with which he protected the territory that ambition had taken. He was not trying to understand the universe so that others could share in that understanding. He was trying to understand it because not understanding it was intolerable, and because the understanding, once achieved, belonged to him. That is the mind we are examining. Not the icon, not the apple tree myth, not the figure on the banknote or the physics textbook. The man who worked alone in a darkened room with a prism, who coded his alchemical notes so they could not be easily read, who launched anonymous attacks on rivals from behind the cover of institutional authority, and who, in his final years, commanded the Royal Society with the quiet certainty of someone who had long since decided he was beyond challenge. The discoveries were real. The mathematics was extraordinary. The physics reshaped how humanity understood motion, gravity, and the structure of the cosmos. None of that is in dispute. But the man behind those discoveries was not the serene, benevolent genius of popular imagination. He was something stranger and more human, isolated, suspicious, brilliant, controlling, and driven by forces he himself may not have fully understood. What follows is an account of how he built, what it cost him, and what it cost others. It begins not with an apple, but with an absence. Isaac Newton was born on January 4th, 1643, by the modern calendar, in Woolsthorpe by Colsterworth, a small village in Lincolnshire, England. He was born prematurely, so small, according to later accounts he gave himself, that he could fit inside a quart pot. His mother, Hannah A. Scoof Newton, reportedly said he was so tiny that nobody expected him to survive. He survived. His father, also named Isaac Newton, had died 3 months before his birth. The elder Newton left no record suggesting particular intellectual accomplishment. He was a farmer, relatively prosperous by local standards, but not a man who left a strong impression on the historical record. His death before his son's birth meant that the younger Newton grew up with no experience of a father, a fact that shaped the psychological architecture of his early years in ways that are not fully traceable but are difficult to discount. When Newton was 3 years old, his mother remarried. Her new husband was Barnabas Smith, a rector from a neighboring parish. Older, financially comfortable, and apparently unwilling to take on the child from his wife's first marriage. Hannah Smith, as she became, moved to her new husband's home. Newton remained at Woolsthorpe, in the care of his maternal grandmother, Mary Ayscough. By any measure, this was a significant rupture. A child not yet 4 years old was separated from his only surviving parent and left in the care of a grandmother in a house that was no longer his mother's. The biographical record does not allow us to know with precision how Newton experienced this, but the evidence of his adult life suggests the wound was significant. He was not a man who formed close attachments easily. He was not a man who trusted readily. The connections he did form tended toward the formal, the structured, the professionally bounded. The kind of trust a child places in a parent who stays. Newton does not appear to have learned that. There is a notebook, surviving, from his school years, in which Newton recorded a list of sins. It is a document that historians have noted with interest, because the sins it lists are revealing of their author. Among them, threatening my father and mother Smith to burn them and the house over them. This is a child recording violence, not as something that happened to him, but as an intention of his own. The stepfather and the mother who left are objects of rage. The rage is carefully recorded, as if cataloging it is a way of managing it. The act of writing it down, confessional, private, precise, is already distinctly Newtonian. He was not, by all accounts, a happy child in the conventional sense. He was not gregarious. He showed early capacity for mechanical invention. He built small models, observed natural phenomena with close attention. But the picture that emerges from the limited sources available is of a child who had learned to keep his inner world separate from the outer one. The people around him were not fully reliable. The world did not give him what it had taken, and so he learned to take what he could from the world on his own terms. His uncle, William Ayscough, recognized that Newton had unusual ability and advocated for his education. It was partly through his uncle's intervention that Newton, who had briefly been withdrawn from school to help manage the Woolsthorpe estate, at his mother's return after Barnabas Smith's death, was eventually sent to Cambridge. Hannah Newton had returned after her second husband died, and for a time there had been a question of whether Newton would become a farmer. He showed no aptitude for it and no interest. The fields and the animals did not hold him. His mind was elsewhere. He arrived at Trinity College, Cambridge, in 1661. He was 18 years old, enrolled as a subsizar, a student who paid for part of his education through service to wealthier students. This was not an unusual arrangement, but it placed Newton in a position of social subordination from the moment he arrived, at an institution structured around status and connection. He had neither in abundance. Cambridge in 1661 was an institution still largely shaped by Aristotelian philosophy. The curriculum that Newton formally encountered there was not at the cutting edge of European thought. But Newton was already reading beyond the prescribed texts, already reaching toward Descartes, toward Galileo, toward Kepler, toward the new natural philosophy that was beginning to reshape how educated Europeans understood the physical world. He was not waiting for the institution to bring him the ideas he needed. He was finding them himself. The pattern was already clear: self-direction, independence from received authority, and a suspicion of consensus that bordered on reflex. Newton did not accept what he was told because he was told it. He tested it. And when his own reasoning led him somewhere different, he followed that reasoning, not toward other people who might validate it, but inward, deeper into his own developing system. He graduated in 1665. He had not distinguished himself socially. He had not formed significant friendships. What he had done was read and think and build, in private, the foundations of the work that would consume the next 20 years of his life. The world was about to close in on him further. It would prove to be exactly the condition he needed. Cambridge in the 17th century was not primarily an institution of scientific research in the modern sense. It was a place for the training of clergy, lawyers, and gentlemen. A place that reproduced the intellectual hierarchies of its time more than it questioned them. The great universities of England in this period were conservative by function and design, and the natural philosophy being conducted at their margins was done there almost in spite of the institution, not because of it. Newton fit poorly. Not in any dramatic or confrontational way. He did not rebel openly against the curriculum, did not challenge his tutors in public, did not cultivate the reputation of an iconoclast. He simply declined to be shaped by what Cambridge offered him in the way Cambridge expected. He read what he chose to read. He worked problems he set himself. His formal studies proceeded in parallel with an entirely separate intellectual life that he shared with almost no one. His tutor during his undergraduate years was Benjamin Pullen, a man about whom history has relatively little to say, which is itself suggestive. Newton's relationship with the institutional mechanisms of his education appears to have been minimal in the meaningful sense. He attended what he needed to attend. He performed what was required. The rest of his time he occupied differently. The notebooks from this period are more revealing than his academic performance. They show a mind that has found a method, read something, test it against other things, extend it further than anyone else has extended it, and continue until the question is answered or the question changes. Newton's note-taking was not passive. He did not simply record what others had argued. He interrogated it, pushed against it, and moved past it. Descartes' mechanical philosophy appears in his notebooks not as received wisdom, but as a set of propositions to be evaluated, found partly useful and partly overturned. He was not building toward a degree. He was building toward a system. The degree was incidental. The system was everything. His social life at Cambridge was, by the evidence, thin. He does not appear in accounts of the conversations and gatherings that animated the intellectual life of undergraduates with strong social instincts. He did not seek out mentors in the way that ambitious young scholars often do, seeking attachment to an established figure who can accelerate their career and legitimate their work. Newton had almost no interest in this kind of professional strategy. He did not want to attach himself to another man's intellectual project. He was working on his own. There is a kind of person for whom solitude is not deprivation, but resource, who draws from isolation the raw material for a particular kind of concentrated work that social engagement makes impossible. Newton was this kind of person. Not by philosophical conviction, not as a lifestyle choice, but as a functional necessity. The thinking he was doing required conditions that other people disrupted. This has sometimes been read as autism, or as depression, or as social anxiety. The historical evidence does not permit confident diagnosis. What it does permit is a description. Newton, through his Cambridge years, withdrew from social engagement not because he was incapable of it. He could be warm, even charming, in the limited contexts where he felt secure, but because engagement diverted resources he was unwilling to divert. His attention was a finite quantity. He was spending it elsewhere. The direction of that attention, by the mid-1660s, was becoming clearer. He was reading Wallace on mathematics, Euclid's Elements, Galileo's work on motion. He was reading Robert Boyle on matter and chemistry. He was reading Kepler. He was building, in his notebooks, a personal synthesis of the most advanced natural philosophy of his time, and already beginning to go beyond it. The specific problems that absorbed him in this period were not randomly selected. They were problems at the frontier. The nature of motion under force, the properties of curves and their areas, the behavior of light. These were not settled questions. They were open questions. And Newton was doing what he always did with open questions. He was pursuing them alone, past the point where others had stopped. He also, during this period, began to read the alchemical literature that would become a central preoccupation for decades to come. Alchemy, in the 17th century, was not the discredited pseudoscience it would later become in the cultural imagination. It was a serious intellectual tradition with a sophisticated body of literature, and many of the most rigorous natural philosophers of Newton's time took it seriously as a source of insight into the hidden properties of matter. Newton took it more seriously than most. He began collecting texts, annotating them, and thinking about what they offered, that the mechanical philosophy of Descartes and others did not. This is worth emphasizing because it is often treated as an embarrassment. Newton's great error, his weakness for mysticism, the crack in the scientific facade. That interpretation misreads both the man and the period. For Newton, alchemy was not a departure from his scientific program. It was part of the same project, understanding the deep structure of matter and force, the hidden principles by which the natural world operated. He did not see a conflict between his mathematical work on motion and his alchemical work on matter. He saw a continuity. By 1665, Newton was 22 years old, holding a bachelor's degree, enrolled for further study, and in possession of a set of ideas that had no parallel in Europe. He had shared them with no one. That was, to his mind, entirely appropriate. The work was not finished. And finished, to Newton, meant something more demanding than it usually does. It meant fully proven, fully defended, resistant to any challenge he could conceive of. He was nowhere near that. He had more work to do. Then the plague came. Cambridge closed, and the work accelerated. In the summer of 1665, bubonic plague moved through England with the indifferent efficiency of a natural catastrophe. London suffered worst, but the disease spread outward into the towns and the countryside, and Cambridge was not exempt. The university dispersed its students and faculty, sending them home to wait out the epidemic. Newton returned to Woolsthorpe. He would remain there, with brief interruptions, for approximately 18 months. What happened during those months has been subject to a kind of reverse mythologizing. The annus mirabilis, the miracle year, the period in which Newton supposedly invented calculus, discovered the law of gravity, and unlocked the secrets of light in a single burst of inspired isolation. The miracle year narrative is an exaggeration shaped by Newton himself, in old age, looking back on a period that had become foundational to his self-understanding. The reality was more gradual, more uncertain, and more interesting. What is true is that the Woolsthorpe period was genuinely productive at a level that has almost no parallel in the history of science. Newton arrived with a set of problems he had been accumulating during his Cambridge years. He worked on them in the conditions that suited him best, alone, uninterrupted, with time that had no institutional shape. There were no lectures to attend, no social obligations to navigate, no university structure imposing its rhythms on his days. There was the farmhouse, the Lincolnshire countryside, his books, and his notebooks. He worked on the mathematics of curves, what we now call the calculus. The specific problems he was solving involved finding the rates of change of variable quantities and the areas enclosed by curves. These were problems that European mathematicians had been circling for years, and a number of them had achieved partial results. Newton approached them more systematically and achieved more general results than anyone before him, developing a method he called the method of fluxions. The name captured something essential about his conception: quantities that flow, that change continuously, that can be described and analyzed in their change. It was a fundamental rethinking of what mathematics could describe. He also worked on optics, specifically on the behavior of light when it passes through glass. He had purchased a prism at the Stourbridge Fair during his Cambridge years, and the question of what the prism revealed about the nature of light had lodged in his mind. At Woolsthorpe, he pursued it. He worked in his room, controlling the light that entered through a hole in the window shutter, projecting it through the prism and onto the opposite wall. observing with close attention the spectrum of colors that appeared. He did not invent the observation of spectral color. Others had noted it. What Newton did was think rigorously about what it meant. The standard explanation at the time, following Descartes, was that colors were modifications of white light, that the prism was doing something to light, adding something to it, changing it. Newton's experiments led him to a different conclusion, that white light was itself a mixture of colors, and that the prism was not adding anything but separating what was already there. Light, in Newton's understanding, was composed of rays of different refrangibility, different tendencies to be bent by glass, and these different rays corresponded to different colors. The prism did not create the colors. It revealed them. This was a significant reversal of the conventional understanding, and Newton pursued it with the methodological intensity that characterized all his best work. He designed further experiments to test the conclusion, passing the separated colors through additional prisms, recombining them to recover white light, building a chain of evidence that he found satisfying in its completeness. He was not a person who accepted a conclusion because it seemed probably right. He needed it to be necessarily right, demonstrated beyond the point of reasonable challenge. And then he set it aside. He did not rush to share it. He wrote it up in his notebooks and held it. The calculus he had developed remained unpublished. The optics he had worked out remained private. Newton, in Woolsthorpe, sitting on discoveries of the first order, made no move to tell anyone. Also, during this period, he began working seriously on the problem of motion under a central force, the problem that would eventually become the law of universal gravitation. He was thinking about the moon, about the way its motion around the Earth could be understood in terms of the same force that caused objects to fall on Earth's surface. The calculations he performed at this time were, by his own later account, tolerably close, but not close enough to satisfy him, and so he set that aside too. This habit of setting aside, of working, finding something extraordinary, and then holding it rather than releasing it, is essential to understanding Newton. It is often interpreted as caution or as perfectionism, or as a strategic desire to present complete systems rather than preliminary results. All of these explanations have some truth. But there is also something simpler and harder to name. Newton did not trust the world with his work. The world had not earned that trust. Other people would misunderstand, or misappropriate, or challenge, or take credit. Better to hold it. Better to keep working. Better to wait until the conclusion was so thoroughly established that no reasonable objection remained possible. He returned to Cambridge in 1667. He was elected a Fellow of Trinity College, and then, in 1669, the Lucasian Professor of Mathematics, a chair that had been held by Isaac Barrow, who reportedly recognized Newton's quality and stepped aside in his favor. Newton was 26 years old. He had, in his notebooks, a body of work that would have made any of the leading natural philosophers of Europe sit up in their chairs. He did not publish it. He gave a series of lectures on optics, lectures that were attended by, according to some reports, almost no one, which appears to have suited him well enough. He worked, he held, he accumulated. The pattern was set. What remained was the slow, often painful process by which the world would eventually get what Newton had built. Not through his generosity, but through persistence, persuasion, and the occasional crisis that forced his hand. The central intellectual achievement of Newton's life was not any single discovery. It was the construction of a framework, a set of principles and relationships through which the behavior of the physical world could be described, predicted, and understood. He was not merely cataloging observations. He was building something with a different ambition, a system that could account for all of it, from the arc of a cannonball to the orbit of the moon, to the tides rising and falling on coastlines across the world. To understand what made this extraordinary, you have to understand the intellectual landscape Newton was working in. The natural philosophy he inherited from his reading of Descartes and others held that the universe was essentially mechanical, that everything could be explained in terms of matter in contact, pushing and pulling through physical collision. This was a productive framework that had generated real advances, but it faced a serious problem. It could not easily account for phenomena that seemed to act at a distance, where objects influenced each other without obvious physical contact. The problem of gravity was central here. Objects fell. The moon circled the earth. The planets moved around the sun. Whatever force was responsible for these phenomena, it appeared to act across empty space without any mechanism of contact that the mechanical philosophy could satisfactorily describe. This was a genuine difficulty, and the leading natural philosophers of Newton's time had not solved it. Newton's approach was characteristically his own. He did not try to explain the mechanism of gravity, did not try to say what it was, physically, that caused one body to attract another. He set that question aside and instead described the relationship mathematically. He established that the force between two bodies was proportional to their masses and inversely proportional to the square of the distance between them. He showed that this relationship, applied consistently, could account for the motions of the planets around the sun, the moon around the earth, and the behavior of objects falling on the surface of the earth. The relationship was universal. It applied at every scale, in every situation. This was a fundamental departure from the mode of explanation that had been standard. Newton was not telling you why gravity worked. He was telling you how it worked, precisely, mathematically, in terms that could be used to predict the outcome of any gravitational interaction you cared to calculate. The mechanism remained a mystery, and Newton was frank about this. I have not been able to discover the cause of those properties of gravity from phenomena, he wrote, and I frame no hypotheses. It was an honest statement and also a strategic one. By refusing to speculate about mechanisms, he made his system resistant to the kind of attack that speculative accounts invite. The three laws of motion that form the foundation of his system were developed from earlier work, Galileo's on acceleration, Descartes' on the persistence of motion. But Newton formalized them in a way that no one before him had achieved. The first law, a body at rest remains at rest, and a body in motion remains in uniform motion, unless acted upon by an external force. The second, the change in motion of a body is proportional to the force applied and occurs in the direction of that force. The third, for every action, there is an equal and opposite reaction. These three statements, taken together, provide the foundation for calculating the motion of any body under any force. What Newton had built was not just a collection of results. It was an architecture. The laws were the foundation. The mathematical tools he had developed, including the calculus, though he presented his arguments in the Principia using classical geometric methods, which he considered more rigorous, were the construction materials. The specific results, the orbits of planets, the behavior of comets, the pattern of the tides, were the building that stood on that foundation. The architecture had a quality that Newton valued above almost everything else. it was self-consistent. One part did not contradict another. The same principles that explained the falling apple, if the apple story is taken as a metaphor, also explained the motion of Jupiter. The system worked at every scale he could test it at, and it predicted phenomena that had not yet been observed. When the predictions were confirmed, the system was strengthened. When anomalies appeared, Newton did not abandon the system. He expanded it. This is the behavior of a system builder, not merely a discoverer. A discoverer finds something and reports it. A system builder finds something and immediately asks, "What else does this connect to? What is the full implication? Where does it lead when you follow it as far as it will go?" Newton was constitutionally incapable of stopping at a partial result. Every finding demanded to be woven into a larger whole. The larger whole demanded to be tested against everything observable. The testing demanded more work. There was always more work. The theological dimensions of this program were not incidental. For Newton, the orderliness of the natural world was not a neutral mathematical fact. It was evidence of design, evidence of a God who had structured creation according to principles that the human mind could, with sufficient effort, discover. The laws of motion were not just laws in the legal sense, they were laws in the deeper sense of being expressions of divine will. The universe ran according to rules because God had made it to run according to rules. And the rules could be found because God had given human beings the capacity to find them. Not easily, not without sustained and rigorous effort, but in principle, with enough of that effort completely. This framing was not unusual in Newton's time. The boundary between natural philosophy and theology was not where we might now draw it. But Newton's version of the theological dimension was distinctive in its rigidity and its specificity. He was not satisfied with a vague sense that God undergirded the natural order. He wanted to know precisely what the natural order was, in full detail, so that the underlying structure of divine intention could be read from it as completely as possible. The program was, in its ambition, essentially unlimited. Newton was not working toward a satisfying conclusion. He was working toward a complete account of the structure of nature, every property of matter, every force, every pattern of motion and change, as an expression of the order built into creation by its maker. He would spend his entire life on this project. He would die without finishing it. That was not a failure. It was the inevitable result of having set yourself a task with no natural endpoint. In January 1672, Newton sent the Royal Society a paper on his theory of light and colors. It was his first significant communication to the scientific community, and it was written in a style that would characterize his public communications for decades. Precise, systematic, and framed not as a hypothesis, but as a demonstrated conclusion. He was not offering a theory for consideration. He was reporting the results of experiments that he believed had settled the question. The paper described his prism experiments, explained his conclusion that white light was a composition of colored rays with different degrees of refrangibility, and outlined the experimental method by which he had arrived at this conclusion. It was well received in some quarters. In others, it provoked exactly what Newton feared: objections. The prism experiments themselves were conducted in conditions that Newton designed and controlled with the care of someone who understood how easily observers deceive themselves. His famous experimentum crucis, the crucial experiment, involved passing light through one prism to separate it into its component colors, then directing a single color through a second prism to see whether it would be further divided or changed. It was not. The individual colored rays, once separated, behaved consistently. A ray of red light passed through a second prism at any angle remained red. It did not split into further colors. This was, for Newton, conclusive. The care he brought to the experimental design was genuine and significant. He was among the first natural philosophers to use what we might now recognize as controlled experimental conditions, varying one factor while holding others constant, systematically ruling out alternative explanations. He darkened his room to control stray light. He used a small aperture to obtain a narrow, clean beam. He repeated the observations until he was satisfied they were stable. This was not the casual observation of a curious amateur. It was methodical, deliberate inquiry aimed at a predetermined standard of certainty. But the certainty Newton believed he had achieved was not universally accepted, and the gap between his confidence and others' doubt produced some of the most illuminating correspondence of his career. Robert Hooke, already an established figure at the Royal Society, responded to Newton's paper with objections. Hooke had his own theory of light, one based on the idea that light was a pulse or vibration, and that colors arose from modifications of this pulse. Newton's conclusion that white light was composed of distinct colored rays was, in Hooke's view, unnecessary. A simpler explanation sufficed. To Newton, this was not an intellectual disagreement. It was something closer to an attack. He responded to Hooke's objections at length, and with a precision that barely concealed his contempt. He restated his experimental evidence. He explained why Hooke's alternative hypothesis did not account for the observations as well as his own. He was right in this, at least in large part. Hooke's theory had real difficulties that Newton's identified accurately. But the tone of the exchange was not that of colleagues working through a disagreement in good faith. It was the tone of a man who found it almost physically painful to have his conclusions questioned. The experience of that exchange, and of other critical responses that followed from European natural philosophers including Christian Huygens, confirmed what Newton already suspected about publication. To put your conclusions into the world was to invite attack. The attacks might be ignorant or motivated or professionally strategic. They consumed time and energy that he would rather spend on further work. And even when he won the arguments, which he generally did, the process left residue. The critics remembered. The disputes lingered. Newton would not forget. He withdrew. For much of the 1670s, he sharply limited his communications with the Royal Society. He had not stopped working. He was working more intensely than ever on optics, on alchemy, on theology, on the mathematical problems that would eventually become the Principia. But he was working in private, and the Royal Society received little from him. When requests came for further papers or results, he deflected or ignored them. He had learned his lesson, and the lesson was, exposure is dangerous. This pattern, work intensely, share nothing, retreat when challenged, shaped the entire trajectory of Newton's scientific career. It meant that the discoveries he made remained unknown for far longer than they needed to. It meant that other natural philosophers, including Leibniz in Germany, were working on similar problems without access to Newton's results. It meant that when Newton's work eventually became public, it arrived all at once, fully formed, apparently from nowhere, which paradoxically made it seem more astonishing and more authoritative than it might have if it had appeared incrementally. The isolation, in the end, may have amplified the impact of the eventual disclosure, even as it delayed it. The optics work was eventually published, but not until 1704, more than 30 years after the original paper. The optics, when it appeared, was written in English rather than Latin, a deliberate choice that made it accessible to a wider audience, and presented Newton's conclusions with a completeness and polish that reflected decades of further refinement. By that point, the questions it addressed had been partly settled by others, and partly not. Newton arrived with his full account as if clearing a table, setting everything in order, leaving nothing unresolved. Control over the interpretation of his own work was never something Newton relaxed. Even in publication, he shaped the presentation carefully, structuring his arguments to lead the reader toward conclusions that seemed inevitable. The Optics ends with a series of queries, questions that Newton poses but does not definitively answer, which are in fact barely concealed assertions. He is telling the reader what he believes to be true while maintaining the formal posture of inquiry. It is a sophisticated rhetorical strategy, and it reflects a man who understood that the appearance of openness could be as useful as openness itself, while carrying none of its risks. Robert Hooke was, by most measures, one of the most capable natural philosophers in England during the second half of the 17th century. He was experimentally gifted, broadly curious, and professionally central in ways that Newton, in his Lincolnshire isolation, was not. Hooke was the Royal Society's curator of experiments, the person responsible for demonstrating phenomena at its meetings, and he moved easily through the social world of London's scientific community that Newton found uncongenial. The two men were temperamentally incompatible in almost every respect. Hooke was sociable, openly speculative, willing to propose hypotheses before he had proven them, and professionally assertive in the way of someone who had spent decades fighting for recognition in a competitive environment. Newton was none of these things. He moved slowly and privately, proposed only what he could demonstrate, and experienced any challenge to his conclusions as something requiring overwhelming response. Their first significant conflict arose from Newton's 1672 paper on light. Hooke's objection was substantive. He had reasons for preferring his own account of color, but it was delivered in a way that, to Newton's ear, suggested that Newton's experiments were not conclusive, and that the matter remained open. Newton could not accept this. The matter was not open. The experiments had settled it. Hooke's refusal to acknowledge this was either intellectual dishonesty or incompetence, and Newton had limited patience for either. The exchange of letters that followed was conducted in the formal register of the period, but underneath the formalities was a clear and mutual antagonism. Newton restated his evidence. Hooke maintained his reservations. Newton did not forgive. This was not a temporary professional friction that cooled over time. It was the establishment of an enmity that Newton would carry for decades, outlasting Hooke and expressing itself in ways that were sometimes petty and sometimes significant. One dimension of their conflict that has received sustained historical attention concerns priority. Specifically, Newton's eventual claim that Hooke had tried to take credit for the inverse square law of gravitation. Hooke, in 1679, wrote to Newton with what he claimed was an analysis of planetary motion in terms of a force varying inversely with the square of distance. Newton's response to this communication was guarded. He was already working on related ideas, and Hooke's claim to have contributed to them, which Hooke made with increasing assertiveness, struck Newton as entirely without foundation. When Newton finally published the Principia in 1687, Hooke was furious. He claimed in meetings of the Royal Society that the inverse square law was his discovery, that Newton had merely developed the mathematical consequences of an idea Hooke had given him. This claim was, at best, a substantial exaggeration. Hooke had, indeed, suggested the inverse square relationship in correspondence with Newton, but he had not demonstrated it mathematically, had not derived the planetary orbits from it, and had not developed anything approaching the systematic theory that Newton had produced. The mathematical content of the Principia was Newton's, in any reasonable analysis. But Newton did not receive Hooke's claims with equanimity. He did not shrug and publish anyway, confident that the work spoke for itself. He responded with the controlled fury of a man whose entire sense of intellectual integrity had been attacked. In the third book of the Principia, there had been a section acknowledging Hooke by name among those who had considered the inverse square relationship. Newton removed it. He was so angered by Hooke's assertions that he could not bring himself to acknowledge him at all, even in the constrained and formal way he had originally planned. The removal of that acknowledgement is a small act in the context of a large book, but it is enormously revealing of Newton's character. He did not do things for strategic reasons alone. He did them because they expressed what he actually felt, and what he felt about Hooke was something between contempt and rage. Hooke had questioned his optics, and now Hooke was claiming part of his gravitation theory. The man was a persistent, unacceptable challenge to Newton's intellectual sovereignty, and Newton responded by excising him. Their enmity also shaped Newton's relationship with publication in ways that are harder to trace but probably significant. Newton's withdrawal from active communication with the Royal Society in the 1670s was partly a response to the experience of having his optics paper challenged. The memory of Hooke's objection, and the others that followed, was part of what made publication feel like exposure. To put your work into the world was to give Robert Hooke, and people like him, a target. Hooke died in 1703. Within months, Newton accepted the presidency of the Royal Society. The timing has been noted by historians without any of them claiming certainty about what it means. What can be said is that Newton did not seek institutional leadership while Hooke was alive. Whether this was simple coincidence or reflected a calculation, conscious or not, that Hooke's presence made the environment uncongenial, we cannot know. What we can observe is the sequence. Hooke dies. Newton moves into authority. The portrait of Hooke that might have hung in the Royal Society's rooms is gone. There is a long-standing tradition, supported by some historical evidence and disputed by others, that the portrait was removed or lost sometime during the period of Newton's presidency. No authenticated likeness of Hooke survives today. We do not know what he looked like. His face has been erased by time, or possibly by something more deliberate. Newton, by contrast, left portraits, busts, and a substantial official record, a man who understood, at some level, that control over how you were seen was itself a form of power. The conflict with Hooke was not incidental to Newton's development as a scientist and as a public figure. It taught him, or reinforced what he already believed, that intellectual life was partly territorial. The territory had to be defended, and that the people who challenged your territory were not, in any meaningful sense, colleagues to be engaged with in good faith. They were threats to be managed. Hooke was the first significant one. He would not be the last. In August of 1684, Edmund Halley arrived in Cambridge. He had a question. He and two other members of the Royal Society, Robert Hooke and Christopher Wren, had been discussing the problem of planetary motion, and specifically the question of whether the inverse square law of gravitational attraction would produce the elliptical orbits that Kepler had described. None of them had been able to demonstrate it conclusively. Hooke had claimed he could, but had not produced the proof. Halley, genuinely uncertain and genuinely curious, decided to ask Newton directly. What happened next has been described many times, and the account given by one of Newton's contemporaries, Abraham de Moivre, who heard it from Newton himself, is worth noting for what it reveals about Newton's method. Halley asked Newton what the orbit of a planet would be if the force attracting it to the sun decreased as the square of the distance. Newton replied without hesitation that it would be an ellipse. Halley asked how he knew. Newton said he had calculated it. Halley asked to see the calculation. Newton could not find the paper, or, in some versions of the account, said he would send it later. He sent it. He also, between that visit and the delivery of the paper, reworked the calculation and expanded it significantly. What Halley received was not just a proof of the elliptical orbit. It was the beginning of what would become the Principia Mathematica, one of the most significant scientific texts ever written. Halley recognized immediately what he was looking at. He returned to Cambridge, encouraged Newton to expand the work further, committed the Royal Society to publishing it, and personally funded its publication when the Society's finances made this uncertain. He was, in the history of science, perhaps the most consequential advocate an unwilling author has ever had. Without Halley's persistence, the Principia might have remained in Newton's notebooks, as so much of his other work had. The writing of the Principia in the 3 years between 1684 and 1687 was an exercise in sustained, concentrated labor of a kind that Newton apparently found as natural as breathing. He worked with near total absorption. His household, in those years, reported that he often forgot to eat, forgot to sleep, worked through the night and into the day, and emerged from his study appearing not to have noticed the passage of time. This was not unusual behavior for Newton. What was unusual was that the work was heading toward an actual publication, that someone he trusted, Halley, was waiting for it, and that Newton had, apparently, made something approaching a commitment. Even so, he almost stopped. When Hooke began asserting priority for the inverse square law, Newton's response included serious consideration of simply not publishing the third book of the Principia, the book that dealt with the physical world, with the planets and the comets and the tides, the book that made all the mathematics concrete and demonstrated that the theory actually described the universe we live in. Without the third book, the first two would have been extraordinary mathematics without physical application. The gesture was characteristic. Newton was willing to deprive the world of his most important results rather than appear to give ground to Robert Hooke. Halley talked him out of it. The process by which Halley managed this is not documented in sufficient detail to know exactly what arguments prevailed, but the result was that Newton completed the third book, and the Principia was published in full. The Hooke acknowledgments were removed, but the book appeared, and it appeared complete. The Principia was written in Latin, in the geometric style of classical mathematics, using propositions and proofs in the tradition of Euclid. This was a deliberate choice, and not only a stylistic one. Newton later said, in an account reported by one of his associates, that he had made the Principia designedly difficult to avoid being baited by little smatterers in mathematics. He wanted his work to be available to those with the mathematical training to understand it, and to be opaque to those without it. The choice of Latin already excluded most readers, The geometric presentation, when he could have used his own more direct calculus methods, added another layer of difficulty. This was not simply intellectual snobbery, it was a defensive strategy. A difficult text is harder to misrepresent, harder to take partial credit for, harder to attack from a position of superficial familiarity. If you wanted to criticize the Principia, you had to actually understand it first. Not many people could. This was, from Newton's point of view, a feature rather than a limitation. The structure of the Principia also reflected Newton's fundamental intellectual disposition: systematic, hierarchical, proceeding from axioms through demonstrations to conclusions, with nothing left dangling, no loose ends acknowledged that he had not already worked on. The three books move from the mathematics of motion in ideal conditions to motion through resistant media, to the application of these principles to the solar system. Each builds on what precedes it. The whole is far more than the sum of its parts, because the whole is a demonstration that the same small set of principles applies everywhere, at every scale. Halley, in writing the introduction to the Principia, described what Newton had achieved in terms that are not excessive even by modern reading. Newton had, in Halley's view, given humanity a mathematics of the heavens. He had shown that the motions of the planets were not mysteries to be attributed to divine caprice or unanalyzable cosmic mechanics, but phenomena governed by discoverable laws that human beings could write down and verify. The universe was, in principle, calculable. When the Principia appeared in 1687, Newton was 44 years old. He had been working on the ideas contained in it for roughly 20 years. He would spend the next 2 decades producing a second edition, responding to critics, and managing the reception of a book that transformed natural philosophy across Europe. He had not wanted to publish. He had been guided, persuaded, and effectively dragged toward disclosure by Halley's persistent advocacy. And, having been forced into the light, he found himself standing in a position he had not fully planned for, the most celebrated natural philosopher in Europe. He did not relax into this position. He did not open up, become more sociable, begin sharing his work more freely. The fame that arrived with the Principia did not change Newton's fundamental disposition. It only gave him more to protect. The reception of the Principia across Europe was not uniform. In England, its prestige was quickly established. The Royal Society recognized its significance almost immediately, and Newton's reputation within the English scientific community rose to a level that was essentially unchallengeable. In continental Europe, the response was more complicated and more interesting. Cartesian natural philosophy, the dominant framework on the continent, was committed to the principle that all physical effects required contact. That action at a distance, the idea that one body could exert a force on another without any physical intermediary between them, was philosophically incoherent. The Principia's gravity acted at a distance. It provided no mechanism. It did not explain how the Earth pulled the Moon or the Sun pulled the planets. It described the relationship between their masses and distances and the force that resulted with extraordinary precision. But it offered nothing about the underlying physical process. This was, for many continental philosophers, an unacceptable gap. Leibniz, in Germany, was among those who criticized the Principia on these grounds. Huygens in the Netherlands expressed similar reservations. The accusation, sometimes stated directly, sometimes implied, was that Newton's gravity was occult, in the original philosophical sense. A hidden force, acting through an unknown mechanism, invoked as explanation without actually explaining anything. Newton's response to this criticism was strategic and, in retrospect, historically significant. He did not attempt to provide a mechanism, because he did not have one and was honest enough not to invent one. He maintained his position that the mathematical description was sufficient, that science was in the business of describing how things behaved, not necessarily why, and that a mathematical law that predicted correctly was preferable to a mechanistic hypothesis that could not be tested. His famous phrase, hypotheses non fingo, I frame no hypotheses, was first published in the second edition of the Principia, and was directed precisely at this criticism. It was not, despite its apparent modesty, a retreat. It was a counterattack. Newton was arguing that his critics were not doing better science. They were demanding something that science could not provide, and calling the demand an intellectual virtue. This reframing was enormously important for the subsequent development of science. By insisting that mathematical description was legitimate even in the absence of mechanistic explanation, Newton was, in effect, defining a new standard for what scientific knowledge looked like. The standard was not mechanism, but predictive accuracy. A theory that predicted correctly was a good theory. Whether or not it explained the underlying why was a separate question, and possibly one that natural philosophy was not equipped to answer. The English scientific community largely accepted this standard, partly on the merits and partly because Newton enforced it through his growing institutional authority. Continental resistance persisted longer. Cartesian natural philosophy maintained its hold in France in particular for several decades. But eventually the predictive success of Newtonian mechanics, confirmed again and again by observation, eroded the resistance. By the mid-18th century, the main outlines of Newtonian natural philosophy were accepted across Europe, and the Principia had become the foundational text of the scientific tradition. What this meant, practically, was that Newton's framework for understanding the physical world had become the framework. The questions it addressed definitively. The questions it left open, questions about the nature of gravity, about the ultimate constitution of matter, remained open, but they were now Newton's open questions, and working on them meant working in his terms. The subsequent century of European natural philosophy was, in significant part, an extended program of verifying, extending, and applying Newton's results. His system was not one answer among many. It was the answer, and everything else was commentary. Newton did not experience this consolidation of authority as external recognition of something he had always believed about himself. He appears to have experienced it as a vindication, but a vindication that required constant maintenance. The authority was not self-sustaining. It had to be defended. Critics had to be answered or dismissed. Challenges had to be assessed, and, where necessary, defeated. The presidency of the Royal Society, which Newton assumed in 1703 and held until his death in 1727, gave him the institutional platform to do this with considerable effectiveness. Royal Society meetings under Newton's presidency were, by accounts from the period, carefully managed. Newton presided with an authority that was not collegial in the conventional academic sense. He was not encouraging open debate. He was chairing a body that had, under his leadership, a clear institutional culture. Newtonian natural philosophy was correct, and the Society's role was to extend and apply it, not to question its foundations. This is not a caricature. It reflects the actual dynamics of an institution dominated by a figure of Newton's intellectual prestige and personal determination. The authority Newton built was real, in the sense that it reflected genuine achievement. The Principia warranted the prestige it received. But it was also constructed, maintained, and defended in ways that went beyond the merely intellectual. Newton understood that knowledge existed in a social and institutional world, and he managed that world with the same systematic attention he brought to natural philosophy. The two projects, building knowledge and controlling its interpretation, were not separate for him. They were aspects of the same program. Historians estimate that Newton wrote more than 1,000,000 words on alchemy. The manuscripts are extensive, covering decades, and they represent a sustained intellectual investment that dwarfs, in sheer volume, his published scientific work. He copied out alchemical texts, annotated them extensively, performed experiments, recorded results, and spent many nights over furnaces that were installed in a small laboratory adjacent to his rooms at Cambridge, working on problems that had nothing to do with motion or optics, or the mathematical structure of the heavens. The existence of this body of work was largely unknown to the scientific tradition that celebrated Newton's physics and mathematics. When John Maynard Keynes purchased a collection of Newton's manuscripts at auction in 1936, he was encountering material that had been kept from public view since Newton's death. Keynes, a trained economist with a broad intellectual range, was struck by what he found. He wrote that Newton was not the first of the age of reason, but the last of the magicians, a formulation that has been quoted ever since, usually to indicate the strangeness of finding such extensive alchemical work alongside the mathematical achievements of the Principia. The framing of Newton as magician is itself a distortion, though a sympathetic one. Alchemy in the 17th century was not magic in the popular sense. It was a serious intellectual tradition with roots in ancient philosophy, medieval Arabic scholarship, and Renaissance natural philosophy. Its practitioners believed that matter had properties and structures that ordinary observation could not reveal, that the outward forms of things concealed inner principles that could be accessed and manipulated through the right procedures. The alchemical tradition was, in this sense, an attempt to understand what we might now call the physics and chemistry of matter, at a level that surface observation could not reach. Newton was drawn to alchemy precisely because it offered what the mechanical philosophy did not, an account of active principles in matter. The Cartesian and Newtonian mechanics of the period described bodies moving under forces, but it described them from outside, as it were, as if matter were passive stuff that forces acted upon. The alchemical tradition suggested something different, that matter itself was active, that it contained within itself properties of attraction and repulsion, of generation and transformation, that were real and discoverable but not accessible through the methods that worked for planetary motion. This was not a naive position. The behavior of certain chemical processes was not easily explained in purely mechanical terms, and Newton knew it. When he observed chemical reactions, substances combining and separating in ways that depended on their specific natures rather than their bulk mechanical properties, he was observing something that his physics did not account for. The alchemical literature, with its elaborate discussions of sympathies and antipathies, of fixed and volatile principles, of the processes of calcination and sublimation and dissolution, offered at least a vocabulary for talking about these phenomena, even if it did not offer a fully satisfactory theory. Newton's engagement with the alchemical literature was characteristic in its thoroughness. He did not sample it selectively. He read widely and deeply, acquiring hundreds of texts, copying out the passages he found most significant, and working to decrypt the deliberately obscure language that alchemical writers used. the obscurity was itself meaningful. Alchemical knowledge was, by tradition, not meant for everyone. It was restricted knowledge, shared in codes and allegories, requiring the right kind of reader with the right kind of preparation to extract its meaning. This was a mode of intellectual practice that was, for Newton, entirely congenial. The secrecy, the coded language, the sense that what was being worked on was too important and too powerful to be shared indiscriminately. These qualities of the alchemical tradition resonated with Newton's deepest instincts about knowledge. He was, throughout his life, a man for whom knowledge was not inherently public. It was something that required protection, that could be misused, that had to be earned by the person who would receive it. The alchemical tradition had a fully developed framework for this view of knowledge. It was not incidental that it appealed to Newton. His alchemical work was conducted in what his contemporaries understood to be secrecy. The laboratory at Cambridge was private. He did not discuss his alchemical experiments with the Royal Society. He corresponded with a small number of individuals, most notably a figure known in the historical literature as Irenaeus Philalethes, who may have been the English alchemist George Starkey, writing under a pseudonym about alchemical matters. But these correspondences were conducted with awareness of their sensitive character. The laboratory work itself, insofar as we can reconstruct it from Newton's notes, involved long series of experiments on metals and their compounds, procedures of heating, mixing, dissolving, and observing the results with the same careful attention he brought to his optical experiments. He was looking for regularities, for patterns that would reveal the underlying structure of matter. He found them in the sense that he recorded consistent observations. He did not find what the alchemical tradition ultimately promised: the philosopher's stone, the transmutation of base metals into gold. But this was not, in Newton's understanding, evidence that the goal was unachievable. It was evidence that he had not yet found the right key to the right lock. The alchemical work informed Newton's later scientific thinking in ways that are difficult to trace precisely, but may be significant. His concept of forces acting at a distance, forces that bodies exert on each other without physical contact, has been suggested by some historians to reflect, in part, the alchemical conception of matter as inherently active. The gravity of the Principia, acting mysteriously across empty space, is more consistent with a view of matter as possessing inner active principles than with the purely mechanical philosophy of Descartes. Newton's physics and his alchemy may have been more closely integrated, at the level of his basic assumptions about nature, than the apparent contrast between them suggests. He never published his alchemical work. He could not have published it, not because it was unrespectable, but because it was incomplete, and Newton did not publish incomplete work, and perhaps also because some things, he believed, were not for public consumption. The pursuit of the deep structure of matter was not, in the alchemical tradition, public knowledge. It was knowledge for the few, transmitted with care, guarded against misuse. Newton had internalized this view. It fit his own dispositions. The million words remained, carefully written, largely in code, in his private papers. They were not an embarrassment. They were a project that was not finished. Newton wrote more on theology than on any other subject. The volume of his theological manuscripts, biblical commentary, chronological analysis, studies of prophecy, extended examinations of early Christian doctrine and its later corruption, runs to millions of words, and sustained his attention for decades with an intensity that equaled his scientific work. This is not a minor footnote to his biography. It is central to understanding what kind of thinker he was. Newton was a man of deep and serious religious belief, but his theology was unorthodox in ways that required careful concealment throughout his life. The specific nature of his unorthodoxy was his rejection of the doctrine of the Trinity, the Christian teaching that God consists of three equal persons, Father, Son, and Holy Spirit, unified in a single divine nature. Newton believed this doctrine was false. He believed it was a corruption of the original Christian teaching, introduced through a specific historical process involving the distortion of Scripture and the manipulation of doctrine in the centuries after Christ. This was not a casual opinion. He worked on the question for years, examining the earliest manuscripts of the New Testament, comparing different versions of key biblical texts, and tracing the historical process by which Trinitarian doctrine had come to dominate Christian theology. His conclusion was that the original Christianity taught by Jesus and his immediate followers did not include the Trinity, and that the Nicene Creed, the statement of Trinitarian doctrine formalized at the Council of Nicaea in 325 COI, represented a departure from the authentic teaching. This was a position with potentially severe consequences in Newton's England. Anti-Trinitarian belief, Arianism, as it was historically called, after the 4th century theologian Arius, who had argued against the full divinity of Christ, was not legally or socially tolerable in any comfortable sense. Newton concealed his views throughout his life. He could not have published his theological conclusions without serious risk to his position at Cambridge, which required regular participation in the Church of England, and without broader social and professional consequences that he was unwilling to accept. The concealment required a certain amount of careful navigation. Newton held the Lucasian professorship, which came with a requirement to take holy orders, to be ordained as a clergyman of the Church of England, which necessarily meant subscribing to Trinitarian doctrine. He obtained, through means that involved a certain amount of well-placed advocacy, a royal dispensation exempting the Lucasian professor from this requirement. The grounds for the dispensation were officially left unspecified. Newton accepted it, and said nothing further about the matter. His theological studies were extensive and serious in a way that is hard to convey without giving them sustained attention. He was not reading theology casually, as a layman with general spiritual interests. He was reading it as a scholar, with the same care he brought to mathematical and experimental problems, checking texts, tracing sources, building arguments, demanding proof. His approach to biblical chronology is a specific example. He worked for years on establishing the correct dates of biblical events, using astronomical data, the records of ancient civilizations, and textual analysis of the Hebrew and Greek scriptures in an effort to construct a historically accurate timeline of the ancient world. This was a serious scholarly project, not a pious exercise, and it resulted in a manuscript of considerable length and sophistication. His conception of God was closely related to his conception of the natural order. Newton's God was not the God of mystical experience or personal devotion, at least not primarily. He was the God of the architect, the intelligence that had designed the natural order with mathematical precision that sustained its operation, and that had built into it the patterns that Newton's science was uncovering. The laws of motion and gravitation were not just mathematical descriptions. They were expressions of divine intention, built into creation at its foundation and discoverable through the kind of sustained, rigorous inquiry that Newton believed he was conducting. This gave Newton's scientific work a theological dimension that was not incidental or embarrassing. It was constitutive. When he worked on the Principia, he was not merely doing physics. he was, in his own understanding, reading the mind of God, uncovering the principles by which God had organized the creation, and demonstrating to humanity that those principles existed and could be found. The universe was not a random collection of phenomena. It was an ordered system, and its order was evidence of its maker. This framework also gave Newton's work on biblical prophecy a different character from what it might otherwise have. For Newton, the biblical texts were another kind of natural phenomenon. Artifacts produced in the ancient world that encoded patterns and meanings that could be discovered through rigorous analysis. The prophecies of Daniel and the revelation of John, which absorbed enormous amounts of Newton's intellectual energy in the later decades of his life, were not merely religious documents. They were coded records of historical and future events, and the code could be cracked by someone with the right method, the right historical knowledge, and the intellectual discipline to distinguish genuine meaning from later corruption. Newton's prophetic studies produced extensive manuscripts, but, again, no publications during his lifetime. He shared his conclusions with very few people. A version of his thoughts on prophecy appeared in an anonymous publication in 1733, after his death. His fuller work on the subject was not published until the 20th century. He did not want it public, and the reasons probably included both the sensitivity of his anti-Trinitarian views and the conviction that prophetic knowledge, like alchemical knowledge, was not for general distribution. The integration of science and theology in Newton's thinking was not the integration of two separate domains brought into uneasy alliance. It was a single intellectual project, the project of understanding the order of the creation in all its dimensions, including the mathematical laws of its physics, the hidden principles of its chemistry, and the prophetic record encoded in its most ancient texts. That Newton was pursuing all of these simultaneously, with genuine conviction that they were aspects of the same inquiry, is what makes him impossible to understand if you separate any one of them from the others. He was not a modern scientist with unfortunate medieval habits. He was a pre-modern thinker of extraordinary capability, working within a framework that unified what we have since separated. To understand him clearly, you have to take that framework seriously. In 1696, Newton left Cambridge. He had spent more than 30 years there, arriving as a sub-Caesar in 1661, serving as Lucasian professor since 1669, and working in the relative isolation that the university afforded. He left to take the position of warden of the Royal Mint in London, a post he obtained through the advocacy of his friend and protégé, Charles Montague, who was at the time serving as Chancellor of the Exchequer. 3 years later, in 1699, Newton became Master of the Mint, the senior administrative position. The conventional interpretation of Newton's move to the Mint is that it represented a retreat from serious intellectual work. A man who had exhausted his creative energy, finding a comfortable official sinecure for his later years. This interpretation is substantially wrong. Newton brought to the Mint exactly the same qualities he had brought to his natural philosophy: obsessive attention to detail, systematic methodology, and an intolerance for imprecision or irregularity that made him a formidably effective administrator. The specific challenge that the Mint was facing when Newton arrived was a serious one. England's currency had been badly debased. Clipping, the illegal practice of shaving metal from the edges of coins and selling the clippings, had reduced the silver content of much of the circulating coinage to a fraction of its face value. The resulting monetary instability was economically damaging, and the government had committed to a massive recoinage. All the old, debased coins would be called in and replaced with new, milled coins whose edges were impossible to clip without visible damage. Newton managed this process with remarkable effectiveness. He oversaw the expansion of the mint's output to levels far beyond what it had previously achieved, established quality controls on the new coinage, and handled the logistical challenges of the recoinage with administrative competence that was, by contemporary accounts, genuinely impressive. He was not coasting in an easy position. He was applying his capacities to a difficult practical problem and solving it. He was also, in his capacity as master of the mint, responsible for pursuing counterfeiters, a criminal matter that Newton pursued with the relentless attention he brought to intellectual problems. He personally investigated cases, interviewed witnesses, gathered evidence, and sent a number of convicted counterfeiters to the gallows. This was not a gentle man performing administrative formalities. He understood that the integrity of the currency required enforcement, and he enforced it. Newton's authority expanded further in 1703, when he was elected President of the Royal Society. He held this position until his death in 1727, 24 years, and transformed the society in ways that reflected both his abilities and his disposition. Under his leadership, the society became more disciplined and more focused. It was also more clearly organized around his own intellectual program. The presidency gave Newton a platform that extended beyond his own published work. He could shape what the society paid attention to, what it endorsed, what it published in its philosophical transactions. He could influence who was admitted as a fellow, who received the society's recognition, and who did not. These were not trivial powers in a world where institutional affiliation and recognition were central to a natural philosopher's ability to work and to be heard. Newton used them. Not crudely, not in a way that was immediately obvious or that generated sustained, open opposition, but systematically, in the way of a man who understood that authority was a resource that required intelligent management. He distributed patronage carefully. He used his network of correspondence to gather information and to shape the way his work was discussed and received. He was, in the language of a later era, an effective political operator, and the operating was as deliberate as anything he did. His position at the Mint provided a separate base of authority, an independent institutional role that did not depend on the scientific community's continued approval. The combination of the Mint and the Royal Society gave Newton a power within English public life that was quite unusual for a man of his background. He had been born the son of a farmer, raised in a modest provincial household, educated partly through service to wealthier students. He ended his life as a knight, knighted by Queen Anne in 1705, the first scientist to receive this honor, and as one of the most powerful figures in the intellectual and administrative establishment of his country. This trajectory was not accidental, and it was not simply the byproduct of his scientific achievements. Newton worked to build his position. He formed and maintained relationships with people who could be useful to him. He understood patronage and reciprocity. He managed his public reputation with careful attention. The man who had spent decades refusing to publish, retreating from engagement, protecting his ideas from exposure, was fully capable of strategic engagement with the institutional world when the stakes and the conditions suited him. What this reveals is not hypocrisy. It reveals a man who had two modes: the solitary, protective, deeply private mode in which his intellectual work was conducted, and the institutional, strategic, authority-building mode in which his public position was managed. These two modes served each other. The intellectual work provided the foundation of authority. The authority protected and extended the intellectual legacy. The combination, maintained for decades, made Newton a uniquely durable presence in English intellectual life. By 1700, Gottfried Wilhelm Leibniz had been one of the most celebrated figures in European natural philosophy for more than 2 decades. He had developed a system of calculus, independently of Newton, working from different starting points and using different notation, and published it in 1684, almost a decade before Newton published anything that explicitly described his own calculus methods. Leibniz's calculus, with its notation of dx and dy for differentials and the integral sign still used today, spread rapidly through the European mathematical community and became the version of calculus that most mathematicians learned and used. Newton had developed his own method of fluxions during the plague years of the 1660s. He had not published it. He had communicated it privately, through letters and through the circulation of manuscripts, to a small number of people. His 1687 Principia used calculus methods in its reasoning, but presented the results in classical geometric form, so the underlying calculus was not immediately visible to most readers. The situation was, therefore, that in terms of publication, Leibniz had priority. In terms of when the work was actually done, Newton had priority. What followed from this situation was the most sustained and damaging intellectual dispute of Newton's career. A dispute that consumed years, damaged reputations, and divided the European mathematical community along national lines for a generation. The dispute had multiple phases, and its escalation was, at each phase, driven partly by Newton himself, though Newton used a method of attack that gave him a degree of cover. He acted through others, and he acted through institutions, while maintaining in his own public communications a posture of reluctant engagement. He was, in the background, anything but reluctant. When accusations of plagiarism began circulating, when the suggestion was made, in various quarters, that Leibniz had stolen his calculus ideas from Newton's earlier, unpublished work, Newton did not simply let these accusations develop on their own. He gathered evidence, wrote analyses, and supplied ammunition to his supporters, who then published it under their own names. He wrote anonymously. He wrote reviews of his own work in the third person, praising his own priority without openly attributing the praise to himself. He was, in a word, managing a disinformation campaign, and he was managing it from behind a facade of institutional neutrality. The most significant formal intervention was the Royal Society's investigation of the priority dispute, conducted between 1712 and 1713. A committee was established to examine the historical evidence and determine who had developed calculus first. The committee produced a report, published as the Commercium Epistolicum, that found decisively in Newton's favor. What was not disclosed at the time, and what the historical record has since established clearly, was that Newton himself had written substantial portions of the Commercium Epistolicum, or at least had played a central role in shaping its findings. He was judge and prosecutor simultaneously, while appearing to be a disinterested party awaiting the verdict of an impartial body. The committee was not impartial. Newton was its effective controller. The Leibniz dispute was not in the end an independent historical inquiry. It was a managed narrative. Newton's narrative, produced under institutional cover, and issued with the authority of the Royal Society behind it. Leibniz, for his part, never accepted the verdict. he maintained his independent priority until his death in 1716, and the historical record supports a nuanced conclusion that the committee's unambiguous finding does not. Both men developed calculus independently, at different times, using different methods. Newton's work was prior in time. Leibniz's publication was prior. Neither plagiarized the other. The discovery was made twice, as significant discoveries not infrequently are. But Newton was not interested in nuanced conclusions. He was interested in his own priority being established definitively and publicly, and he was willing to use every institutional and personal resource available to him to achieve that result. The fact that his intellectual claim was legitimate did not constrain the methods by which he pressed it. The Leibniz Dispute also had a significant negative consequence that Newton may not have fully appreciated, or may have been willing to accept as a cost. It severely damaged relations between British and continental mathematics for several decades. Newton's notation for calculus, his dot notation, using dots above variables to indicate rates of change, was less flexible and harder to use than Leibniz's notation. But British mathematicians, loyal to their national hero and hostile to Leibniz and his tradition, continued using it long after the continental tradition had moved on. This meant that British mathematics fell behind continental mathematics for roughly a century, a period in which the great advances in the Newtonian program were made largely by continental mathematicians working in Leibniz's notation. Newton won the priority dispute. He probably did have priority. He also, in winning the way he chose to win it, damaged the mathematical tradition he had done more than anyone to create. This is characteristic of the late Newton, the exercise of power for the protection of territory in ways that were effective in the short term and costly in the longer view. He was not a man who took the long view in disputes. He was a man who took the decisive view. The territory had to be defended, completely and immediately, and the means of defense were secondary to the result. He had always operated this way. The difference in his later years was that he had the institutional power to make that operation truly effective and truly damaging. In the last 2 decades of his life, Newton was the most famous natural philosopher in Europe. His name was invoked as a standard of intellectual achievement. His work was taught in universities across the continent. Poets wrote odes to him. Philosophers took his method as a model for inquiry in fields far from physics. He was not just a scientist who had made important discoveries. He had become a symbol of the power of human reason, of the capacity of mathematics to unlock the secrets of nature, of the possibility that the universe was comprehensible. He appears to have found this largely beside the point. The famous face, the portraits from his later years show a heavy man, white-haired, with an expression that might be read as serenity, but is more accurately described as distance, gives little away. Newton did not write about his inner experience in ways that make it easy to access. He was not a man who reflected on his emotional life in his correspondence, or kept a diary in the confessional sense. What can be inferred is that the solitude that had characterized his working life did not dissolve in old age. It deepened. He lived in London from 1696 onward, but London did not change his fundamental patterns. His household was managed by his niece, Catherine Barton, who was his social representative in a world that Newton himself could not fully inhabit. She attended the social functions he could not. She managed the domestic life he paid no attention to. She was, by various accounts, a witty and capable woman who navigated London society with ease and occupied a position in Newton's household that gave her both dependency and authority. Their relationship was close in the limited sense that Newton's relationships could be close. She was useful to him, and he was dependent on her practical management, and there was evidently affection of some kind. His friendships, such as they were, remained narrow and formal. There were correspondents, protégés, official associates. There was no intimacy of the kind that most people develop over the course of a long life. Newton had never learned that kind of intimacy, or had decided early that it was not worth what it cost. By old age, the alternative had fully taken hold. He was surrounded by the trappings of fame and separated from personal connection by habits of self-sufficiency too old to change. His intellectual work, in the years after the Principia's second edition appeared in 1713, turned increasingly toward the theological and prophetic studies that had always run in parallel with his physics. The Optics, published in 1704, was his last significant scientific publication, and its closing queries, those barely concealed assertions about the nature of matter and force and the active principles embedded in creation, gestured toward a research program that he would never fully execute. He continued revising and extending his prophetic manuscripts. He corresponded on matters of theology with a small number of trusted individuals. He did not publish this material. The Royal Society continued to occupy his time and to provide a stage on which his authority was regularly exercised. But the meetings, the correspondence, the management of institutional life, these were, in his later years, more occupation than engagement. He was going through motions that he had learned long ago, performing the role of president and authority, without the animating urgency of genuine intellectual discovery. He also continued, into very old age, to nurse his disputes. The Leibniz priority question was, by the time of Leibniz's death in 1716, technically settled. Newton had won. But Newton continued to revise and amplify the materials of the Commercium Epistolicum, continuing to work on the case that was already decided, as if the verdict required perpetual reinforcement. This was not simply thoroughness. It was the expression of a psychological disposition that could not let a battle go even after the battle was won. There is something both admirable and melancholy about the late Newton. The relentlessness, the refusal to soften into comfortable old age, the continued commitment to the same projects, the same defensiveness, the same standard of completeness that had driven him since his 20s. He had not changed. He had aged, accumulated authority and fame, and remained, at the core, the same isolated, rigorous, controlling presence he had always been. He died on March the 20th, 1727, in his 84th year. He had been ill for some weeks before his death. According to accounts from those present, he remained coherent and clear-minded until close to the end. He did not, apparently, make a deathbed religious conversion or recantation. His privately held anti-Trinitarian views remained privately held. He was given a state funeral and buried in Westminster Abbey, an honor reserved for the most significant figures in English public life. On his tomb, Alexander Pope's famous epitaph was eventually proposed, though not inscribed there. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. It was exactly the kind of mythologizing that Newton's actual career resists. He did not come from nowhere and illuminate everything. He worked for 60 years, alone, in secret, with fury and control and systematic brilliance, and built something that required all of that to build. The poetry is easier than the truth. Newton himself would probably have found the truth more satisfying. The apple story persists because it is useful. It compresses something genuinely vast, decades of sustained, solitary intellectual effort, into a form that fits in a sentence. It transforms a complex history of obsession and control into an accessible narrative of inspiration. It makes Newton comprehensible as a type, the lone genius struck by the universe's secrets, sharing them generously with an eager world. None of this is accurate, and the inaccuracy is not incidental. The apple story does not merely simplify Newton, it reverses him. The man it describes, open, surprised, giving, is nearly the opposite of the man the historical record reveals. What Newton actually built was not just a physics. It was a system, an integrated framework for understanding the physical world that connected mathematical tools, experimental methods, and cosmological conclusions in a mutually supporting structure. The system was extraordinary in its scope and, within its domain, its accuracy. It described the behavior of the physical world at scales from a dropped stone to the orbit of Saturn, and it described them correctly, in the sense that its predictions matched what careful observers actually found. But the system was also built with a particular intellectual culture embedded in it, one that reflected Newton's own dispositions and that he actively promoted as his system spread and became authoritative. The culture was one of rigor without mechanism, of mathematical description as sufficient explanation, of experimental method as the arbiter of truth, and of authority as the proper reward for those who could master and extend the system's results. These cultural commitments were not neutral. They carried Newton's personality into the scientific tradition that emerged from his work. The emphasis on mathematical proof over qualitative argument, the insistence that hypotheses not supported by experimental evidence should be set aside, the assumption that the natural world was sufficiently ordered to be described in precise mathematical terms. These were not self-evident principles of inquiry. They were positions that Newton's success had made standard, and they had made it standard partly through the sheer force of that success, and partly through Newton's deliberate management of the institutions that shaped what counted as legitimate science. The Newtonian tradition that dominated European and eventually global natural philosophy for the better part of 2 centuries was, in this sense, Newton's creation in a more complete sense than its content alone would suggest. He had not merely discovered the laws of motion. He had established a way of doing science, a set of standards, methods, and intellectual values that bore his imprint and that shaped the work of those who came after him far more fundamentally than any specific result. The Alchemy and the Theology, which the tradition largely set aside, are essential to understanding what Newton was actually doing. He was not a physicist who happened to have eccentric hobbies. He was a natural philosopher pursuing a unified program aimed at the total understanding of the created order, its mathematical structure, its material constitution, its historical record in scripture and prophecy. And the parts of that program that did not fit the emerging scientific tradition were simply discarded by the tradition, while the parts that fit were absorbed and codified. The discarded parts are interesting precisely because they show the limits of the absorption. The Newton who became the founder of modern science was not the complete Newton. He was a selection, the parts that the 18th and 19th centuries found useful, organized into a founding narrative that served the needs of a scientific tradition seeking its own legitimacy. The real Newton resisted that narrative from the beginning, not in the sense of conscious opposition, but in the sense of being too complex, too committed to too many things, to fit into any clean story. He was a man of the 17th century, pre-modern in his cosmology, in his theology, in his understanding of what the natural world was and what it meant to understand it. He happened also to be someone whose mathematical and experimental achievements were so extraordinary that the following centuries could not ignore them. The tradition that took him up had to do a certain amount of selection and simplification to make him fit. The selections are understandable. The simplifications are not always harmless. When Newton is taught as the originator of a value-neutral, purely empirical science that simply reads the facts of nature and reports them, the actual process by which knowledge is produced, contested, defended, institutionally managed, shaped by the personality and situation of its producers, is hidden. Newton's life is, in fact, one of the most vivid illustrations available of how knowledge is produced. Not by inspired individuals receiving truth from nature, but by obsessive, competitive, strategically intelligent human beings, building systems under conditions of uncertainty, rivalry, and personal investment. So intense it might better be described as psychological need. He built what he built because he could not stop. Not because the universe wanted to reveal itself to him. Not because he was specially chosen or gifted in some mystical sense. Because he had the capacity to sustain attention at a level that few people can match. And because the problems he had chosen would not let him go. And because stopping, before the answer was found, before the system was complete, before every objection had been addressed, was simply not something he was constitutionally able to do. That is, in the end, the most honest thing that can be said about Isaac Newton. He did not receive knowledge. He extracted it, through force of attention, through relentless method, through the willingness to spend a lifetime in the work, from a universe that did not give it easily. And, having extracted it, he held it close, defended it jealously, and released it only when circumstances gave him no other choice. The apple did not fall. He reached up and took it,